Okay. So good morning, everyone, and thank you very much for giving me the opportunity to be here. I guess when I received the invitation to participate in this nice event, it must have been that by association I am connected with the tree of Venkat, and I feel honored to be here and be able to celebrate with Venkat this milestone. But it is actually my other second half that is associated with the tree. So since Professor Yannis Androulakis, my husband, actually did a master's with Venkat at the early ages of artificial intelligence. I did then pick, the subject that actually I thought that it would have been a very interesting one from Venkat's perspective, and one that actually we have worked together in the area in the context of pharmaceutical manufacturing. So try to give, a little bit of perspective why process systems engineering rediscover the artificial intelligence, including, of course, machine learning, surrogate models, and how this can be applied to different applications. So I don't promise that I will stay on time, but Stratos, I think, is going to be here trying to bring me back. So this is my group, and I do like to start always with acknowledging the students that are working with me on this, because those are the people that are doing the actual work. And so this is actually, a nice day in University of Delaware, so we got to get out and get pictures without masks. So why now we started looking again at the artificial intelligence, and I have been in many of Venkat's talk of how he thinks that actually a number of different circumstances come into the picture, and then that's why the proper time appears. And indeed, that's the case, and we've seen that there are a number of developments that actually made this, the implementation of different tools that are connected with the fourth industrial revolution. And this is the fact that actually we can get a lot of data, and those data are connected, and actually we can store the data. We have close to unlimited computational capabilities to try to get to store and get the information out of the data. So, of course, process systems engineering looked at those things of how we can get the most out of this information, and first of all, how we can extract information from data, and how we can use it for different applications. So we looked a little bit at what was happening the last few years. And there are, if you see here in this table, there are a number of different policies and initiatives, both from different agencies around the world, but also in industry, that are trying to embrace Industry 4.0, the different tools, and try to see, how they can utilize this to be able to adapt and predict better different situations, and be able, of course, to be profitable under different situations. So this is basically from McKinsey report, actually this year, 2021, which shows that basically different industries have been able to address the fact that you have different situations under pandemic, if they had some type of implementation of Industry 4.0 capabilities. And depending on, in different sectors of the different companies. And they have reported that they have, of course, better flexibility and agility to go to the scaling of operations. They have been reliable to deliver to the customers, and so on. And of course, this trend is also it can be seen in a number of different applications. This is from Web of Science, and we have seen an increase of the number of publications of 20-fold over the years in 1 decade. We have seen the 13-fold increase in terms of publications that deal with big data, and 10-fold in terms of publications that deal with machine learning. So there is definitely a lot of interest, there is definitely a lot of ideas, but there is also the need from the industry to apply those tools to solve problems that are related to disruptions of their productivity and to the supply chain. So, of course, I mean, we need to look a little bit more closely in terms of the modeling, how we can utilize better the data and why do we need more data, and what we can do with the data that we have in order to be able to extract information, being able to get this information and transform it to knowledge, and that's basically a lot of contributions that Venkat has done over the years, because it's not only, to have the information, it's just how you can utilize this to do something about it, right? So how you can bring this into the picture of the real situations. There are a number of different techniques that appear in the literature and I'm going to focus just on the simple surrogate models and hybrid models that take the data from different resources. It could be laboratory experiments, it could be data from the plant, or it could be data from large-scale simulations. Those data can be connected to different parameters that you have or different process variables. And then we utilize all of those, a plethora of tools to be able to extract, again, some information about the system. And this information could be, and I'm going to show you some applications about that, if the process is feasible or not feasible, how can I use demand forecasting to do predictions, or how can I use very detailed computational modeling to be able to produce the better products. So the models that we have seen that comes from this community are either black box models that basically deal with the input-output data, and we're trying to fit some forms, some functions in order to explain what is the connecting function between the inputs and the outputs, or different combination of hybrid models. So we can get some idea about different functional groups and incorporate this with our understanding of the data. I do like to point out to the work that Professor Fani Bukuvala is doing, and actually presented yesterday about the work towards how you can do that more efficiently. So we have looked at this problem, and we have actually derived two different ideas of how you can do that, either by doing just a sampling and then build the models, and the models could be stationary, or using some type of adaptive sampling to be able to much more intelligently sample the space and produce using some type of criterion of where these points should be, then stop and then use the model. So if the question is adaptive or not adaptive, then the answer is it depends. Right? So if we have in the case where you can do both, then trying to extract the best by utilizing the fact that you have just a limited type of, that's a limited computational resource, it's better to do adaptive. But this is not always the case. So when you don't have this luxury, And this is where you are having only historical data, so you cannot get to produce more data as you go. Then, of course, I mean, you can just use the data that you have and build out of this. But when you have the capability of doing some more experiments, then this adaptive framework can help you identify where to put that. So with that in mind, with this a little bit general framework, I would like to go through a few applications. Applications that actually stem in the area of pharmaceutical manufacturing, something that I had the pleasure to interact with Venkat through through the ERC, that there was a collaboration between Purdue, Rutgers, and GIT, and University of Mayores in Puerto Rico for 10 years. So we have the pleasure to interact and do a number of different nice work, as Rex pointed out. So I will start with the area of biological manufacturing. Not this is small molecules that we worked with, but I will use an example on the small molecules too. So in the biopharmaceutical manufacturing, and I think Richard is going to talk a little bit about that later on, we are producing complicated molecules, proteins, and we are producing this using, as I show here, you can do that using the continuous line, using perfusion bioreactor, and then continuous downstream processes, or you can go the more traditional way of producing this in a batch mode. One way or another, you cannot avoid the fact that actually the reactor, it's a very complicated process because it involves all the nice things that we're learning as chemical engineering, all the transport phenomena, multi-phase systems, but also it involves real life, which are the cells, which are the ones that are producing the final product. So a model should be able to capture not only the transport phenomena, but actually going into the heart of the production facility, which is the cell. So it should include the metabolism, and it should include all the different details in terms of like how this final protein is produced, which means, what is the glycan structure, which is going to give you the efficacy of the drug that you are producing. So a model is a complicated one, so that's why even if you come with a very detailed mechanistic model, you need some type of information extraction so you can better utilize, optimize, and so on. So that's basically what we have been working, and in my group there are 2 papers actually given in this conference from students in my group, Young and Giant. Actually, Giant just gave a talk like a couple of minutes before that. And we're trying to be able to, again, capture this computational fluid dynamics, but also the metabolic model, and then produce a surrogate model that can extract the necessary information which is needed. We're using Gaussian process estimator here that then can predict the behavior of this system at different operating conditions. So basically, if you were able to do that, having the integrating model so that we can capture the different effects that we see, and then optimize it. So we can optimize the feeding schedule. We can optimize aeration, agitation policy, and then, of course, being able to keep the cells alive and be able to produce the right product. So that's an example of how you can utilize surrogate modeling to be able to capture information from an expensive simulation. The next example, again, comes from the pharmaceutical industry and goes more into the development of the design space, which is given in our community the feasibility space. So we're trying to identify where, in terms of the operating conditions, where we are feasible, where we are able to operate and get the product with the right specifications in terms of product quality. So we can look at this system, and this is a work that we have done over the years in the context of the ERC that I mentioned before, of identify, using data, the feasible space, of course, using the ideas of flexibility analysis, going back to Professor Fludas and Professor Ignacio Grossman, that identify the actual enclosure of where the process is feasible. So, okay, where the data is coming into the picture is that this is a complicated design space. So most of the theories that exist gives you very good results, but only when you have convexity assumptions. Here we don't have convexity assumptions. We don't know even the shape of the feasible space. So we were operating under the conditions that, okay, I can get some data from running my expensive computer simulators and then try to see how efficiently I can find out where I am feasible to operate. This is what we're doing here with an expected improvement function, which basically tries to put points more closely to the boundary of the feasible space and not all over the place, and then building the final model. So we have applied that, and I'm glad that Rex came before me because he gave a nice introduction of the work that the group has been doing over the years of trying to model the production of solid-based drug manufacturing. This is the line as it has been built, both instances at Purdue University and Rutgers University. And now we were looking on this in terms of the input-output mapping and in terms of identifying the design space. The space that all those input parameters, including, for example, flow rate of the API, the excipient, blender speed, and fill depth, all of those are operating conditions of the manufacturing line, how we can adjust this but still be feasible. And if you do the analysis as I presented, you identify the range of conditions, including within these red lines, that the design is feasible to operate. So if it is large as this one, then you have more flexibility. But if it is narrow like that, you have to apply very close, tight control so as to be able to guarantee quality. So with that, I had another example, but I see I'm running out of time. So for those of you that are interested, my student presented this. Is a work that we're doing in the area of biomass conversion to chemicals and fuels, and I thought that Venkat would have been interested in this. But again, due to the lack of time, I will not present this, but I do like, of course, to acknowledge financial sources, but most of all, we're here to celebrate Venkat's birthday. As you see here, I didn't put any numbers, right? So number is a number, so it doesn't matter. We're celebrating Venkat and to wish happy birthday to many more productive, joyful years. And with my wish, when I grow up, I would like to be like you.